Preliminary analysis. Before you can analyze, you got to analyze. Before performing any statistical test, it is a good practice to make some descriptive statistics in order to have a first overview of the data and perhaps have a glimpse of the results to be expected. This can be done via descriptive statistics or plots. Descriptive or summary statistics. We already started that. We already started summarizing the data above just to kind of get a rough look at it. But now we want to actually get a little bit more. We want to get the means not just by variable, but by group, right? So if we want to keep it simple, we can compute just the mean for each subgroup using the aggregate function. Note that the syntax is similar to running the AOV model. So if we want to look at the mean by group, not just the mean for sex and the mean for species, but the mean of each species, male and female, right? We want to know the mean weight for male Adelaide, female Adelaide, the mean weight for male Gentoo and female Gentoo, right? Each one of those. If you were going to try to do that in Excel, it would actually be kind of a pain to do it unless you used a pivot table. If you know how to use a pivot table, it's a snap. But you've already got your data in R, you're doing your analysis here, you're writing your report, just use the aggregate function and you got it like that. And here's how you do it. Use this code, right? You can change the X and Y variables. This will work. Aggregate, right? You aggregate it, body mass, there's your Y, right? As a function of species, there's your first X, plus sex, there's your second X. And then what are you running it on? You put your comma, data equals dat. You could put this all in one line. I just broke it up into 3 lines. And what do you want to get out of this? You want a function, mean, fun with a capital F. That's some mean fun you got right there. Okay, and then you get this cute little table. This cute little table that says like species, sex, body mass. And you're like, oh, there's Adelaide. And there's all the female, and there's the body mass. And then there's the chin strap, female, there's the body mass, right? And like, let's say, oh, wait, I didn't really want it to be all the females grouped together or in the males grouped together. I wanted it to be by species. Well, you could just change this around. You could just make it go back to the code and say sex plus species and then run it. Okay. And now we can say we've got male and female of the Adelaide body mass, right? Male, female, Adelaide body mass. And you can compare them. Okay. And I mean, maybe the whole point of this analysis is that it's hard to tell the males from the females. And that's why we were missing data. We want to see, well, are males really different than females in terms of body mass? Like, could you just kind of look at it and see, oh, the males are bigger. So if it's bigger, it's probably a male. You know, it helps to determine the species that way. Okay, male and female chin strap, male and female Gentoo. And you can already kind of start to just see some differences. The Gentoo males are 5,484 grams, whereas the chin strap males are only, they're like less than 4,000. They're 3,938. And then the male Adelaide is about 4,000. So even just looking at it, you can start to see, okay, well, the smallest penguins, the littlest little penguin is the female Adelaide. And it's a lot smaller than the female Gentoo, but is it significantly smaller? And it's not that much smaller than the chin strap. It's like roughly 200 grams smaller than the chin strap. But is that a significant difference? 200 grams? Not that much, less than a pound, right? So are they different? Is that a difference? Depends a lot on the variances. Okay, so let's include the mean and the standard deviation so that, or let's include the standard deviation with the mean here so we can get an idea. Well, it depends on the variance, right? Okay, so let's load the dplyr package. I'm going to run the whole chunk here so Yeah, load the dplyr package, then we know. If I run the whole chunk, again, I put this warning equals false, so we don't get all that red gobbledygook, because we don't need it. It's not giving us good information. It's just, I mean, it's good, but we don't need it right now. And then what we're going to do is group by. And what are we going to group? We're going to group the data. We're going to group by sex and species. Excuse me. Actually, let me change this again to species by sex, because I think that's actually more interesting to look at it that way. Okay, right? And we're going to summarize. We're going to get the mean. And here, notice I put this round. So we're not going to get so many decimal points. Round of the mean of the body mass, and then NA removed equals true. And I think I did this before I cleaned the data. Now I'm embarrassed because I actually didn't clean my data and I ran through the code and then I went up and cleaned the data at the end, which exactly what I told you not to do. And now I've got all this gunk here where I again forgot to use my clean data set. I'm using DAT instead of DAT-C. So you know what? Let's change this. Let's say DAT_C. And let's run this again. And now we won't have the NAs in our handy table. It looks a lot cleaner. And we can see that we are comparing species of Adelie, male and female. There are the means, and then there's the standard deviation. And when you have a really high standard deviation, you're not as likely to have those differences between groups. So, interesting. Again, you can see our standard deviations are all roughly similar. They range between 269 and 362. So homoscedasticity definitely good. You could have looked at it that way too.